Hey, welcome back. Today we're taking a look at, or continuing to take a look at the quantum mechanical model. And today, day 3, kind of be the last day we look at this stuff. We're going to look at some exceptions to the rules. So every once in a while we have to break the rules. So starting off with valence electrons has become more important in a couple of chapters. Valence electrons are the electrons that are found only in an atom's outermost energy level. So here's, again, going back to kind of the Lewis model. Sometimes it's easiest to see it this way. We have the energy level 1, the energy level 2, and then here is the valence electrons, only the outermost electrons. So this atom has 7 valence electrons. This atom over here only has 1 electron in its outer shell, so only 1 valence electron. When we take a look at electron configurations, keep in mind that sometimes we go up a level, like 4s, and then back to 3d. So when we're filling in the 3d, technically there's still only 2 valence electrons, because we've got 2 in the outer energy level. So that 3d is never a valence shell, never an outer shell, because we've got the 4 outside of it, around it. Alright, so that is valence electrons. And again, we'll come back to those, and those will be more important in a few chapters from now. But next up, we have stability. Some configurations are more stable than others. So we've got this periodic table here. And again, hopefully by now you guys are fairly aware of the designations. In this first column is going to be an S1. It has its last electron and an S. Second one is S2. They have 2 electrons in the S. We'll go to D block, D1 through 10. We've got F down here on the bottom, F1 through 14, and P 1 through 6. So everybody in this column here has 6 electrons in their P orbital. So the most stable arrangement, all atoms would love to have a full energy level, and that's P6. So over here at the end of the table, you've filled up your energy level when you get to P6. These are the noble gases. You've probably heard of them. They're inert. They don't react. And one of the reasons is because they're full of electrons. They don't need to react. They don't need to share. They don't need to gain. They don't need to lose. P6 is the ideal place. That's like the #1 place. We give him the blue ribbon. If you guys are familiar with sports, blue is usually the ribbon given for first place. That is the best possible place to be. But not everybody can get to P6, excuse me. So there's second place winners also. The next best place to be is to have a full sublevel. So S2, D10, F14, as long as you have that entire sublevel closed off, that's not a bad place to be. So they get the red ribbon, the second place ribbon. That's a pretty stable configuration to have a full sublevel. Finally then, third place is a half full sublevel. So all up arrows, no down arrows at all, but 1 up arrow in every single orbital. And those are the S1, D5, P3, and F7. So those are the third best places to be with the half full sublevel. Any other consideration, any other configuration is not important at all. So it's not like D4 is any better than D3, and D6 is not better than D7. So those are the 3 winners. P6 is the winner. S2, D10, and F14 are the second place winners. And then the half full sublevels, S1, D5, P3, and F7, those are the third place winners. Alright, so all of that in mind, we can sometimes break the rules. So the off-ball principle says you have to fill up electrons in the lowest possible energy level first. But sometimes, to get to one of those more acceptable configurations we just looked at in the last slide, Sometimes some elements will take an electron from the S and add it to the D. Let's take a look at some of those examples. Now there's 5 you're responsible for knowing. Chromium, molybdenum, copper, silver, and gold have the exceptional electron configurations. Chromium first. If we were to do the electron configuration for chromium, here's what it would look like. And you can notice right there, chromium is 3d4. He's 1 electron away from having a half-full sublevel. So what chromium will do is he'll take 1 electron from the 4s, and now 4s is half full. This is not a bad place to be because this is a half-full sublevel. And he adds that electron transfers over here, he adds it to the 3d. So now chromium has 2 half-full sublevels. And this is actually the correct, the more stable configuration for chromium. So it looks kind of weird. We've got 4s1, we've got the empty orbital there, we've broken the off-ball principle, but we've satisfied half-full sublevels, so this is the more stable configuration. So if ever you see chromium, this is the correct electron configuration, the one on the bottom here. The electron configuration, again, it looks weird, 4s1, we're used to seeing s2 at this point, but the correct way to state it is 4s1, 3d5. Kind of a heads up, if you're looking at your periodic table, chromium and molybdenum and copper are the d4s. You will never have a d4. If you end up with a d4, you know you've done something wrong. So d4, no good. Put an X through those in your periodic table. Don't end on d4. Always take an electron from 4s and make it d5. Copper is 1 away. We can see here's, if we were to do the orbital notation, as normal, we'd see we're 1 electron away from a full shell. So just as we did up above, we're going to take 1 electron from the 4s. Again, we still have a half full sublevel, so that's okay. It's not terrible. And now we have a full 3d. Again, that's more stable. So for copper, who has d9, and that goes along with silver and gold, Ag and Au, again, same thing. You should never end with d9. Never end with d9. Just take 1 of those electrons from the 4s, bring it over, and put it and make it d10. This is the proper orbital notation for copper. Correct electron configuration, again, 4s1, 3d10. That's the same thing for silver and gold, except it'll be 5s1, 4d10, and 6s1, 5d10. But never end in d9, that'd be copper, silver, and gold. Never end in d4, that'd be chromium and molybdenum. So that's all there is today. One last little trick here, the exceptional electron configurations.